Next up is PhillipThompson. Phil is the Director of the Center for Environmental Justice and Sustainability and a professor in the College of Science and Engineering.
Thanks, Sarah. Good afternoon, everyone. Thanks for joining us today. I too want to thank Seattle University for supporting my research. So arsenic occurs naturally around the world, and it contaminates groundwater, which millions of people consume every single day. So this research is looking to develop an inexpensive way for people to remove arsenic from their drinking water. This research is also related to indoor air quality. So if you add up all the people that die because they don't have access to safe water every year, it's about 1 million people. So multiply that number times 5. So 5 million people die every year around the world because they have bad indoor air quality, because they're cooking over indoor fires like you see here. So to help with indoor air pollution, people can use these pyrolysis cook stoves, which, as you can see on the right here, have very low emissions. One unique feature is that after you're done cooking your food, you have charcoal remaining. So that charcoal, it tends to have a negatively charged surface. So it can be used to remove heavy metals like mercury from drinking water. Usually it's really hard to remove metals from water, and this is an easy way to do it. So this process, it uses a waste product, wood chips, as a fuel for cooking. So I just love this idea of taking a waste product and using it in a beneficial way. So we take the wood chips and we can weigh them out, and we can soak them. So I should mention, I did this research in my backyard this summer because of access to the labs was a little difficult due to construction and COVID and so forth. And so the idea is we're going to take these wood chips and we're going to soak them in magnesium chloride solution. So we're hoping then that this magnesium chloride this magnesium will impart a positive surface charge onto the biochar so that we can remove negatively charged ions such as arsenic. So you can see I'm drying the wood chips after they've been soaked in the magnesium chloride. It's a little delay here. So we go ahead and burn the wood chips. We create this charcoal. We process the charcoal with a mortar and pestle. We run it through some sieves so that this charcoal can meet American Water Works Association standards for filters, for carbon filters. And so I went ahead and I constructed these inexpensive filters that they mimic these ceramic filters that are made by Potters for Peace. So on the bottom of my PVC column here, I have a ceramic filter, and then I put my enhanced biochar. So that's the biochar that has a positively charged surface in a layer on top. And the good news is that it works. So we started with a concentration of about 2 milligrams per liter of arsenic. That's the average arsenic concentration in groundwater in India. So the controls, we're not seeing any removal there. So the untreated biochar, so that's just a plain old biochar, it's going to have some natural capacity to remove the arsenic from the drinking water. But then our enhanced biochar, that positively charged surface biochar, can significantly remove the arsenic from the drinking water. So that's now one caveat here is that we don't quite meet the maximum contaminant level that's set by the Environmental Protection Agency of 10 parts per billion. So we're right around 20 parts per billion here. And so what we need to do is we need to have a little thicker layer of carbon in our filter. We need to add more carbon to that filter. So that's one of the things we're looking at now. We're optimizing the design of that filter. One kind of downside is that this process imparts a little bit of color to the water. So there on the right, you can see there's a little bit of color. Now that color could be removed with an activated carbon or your Brita water filter at home would remove that color. So, but that's just an additional note. So normally we do research in the lab and then we go on to the field. So we're doing that just in reverse here this year. So we did the lab research in the summertime, or I'm sorry, the field research in the summertime. And now here this fall, I have a student that's working with me to look at some of the some of the more detailed analysis and experiments. And so here's an example of what we call a absorption isotherm that helps us determine the capacity of the biochar to remove arsenic. And so the results so far indicate that a family of 4 would be able to produce enough biochar every day from their daily cooking to treat their drinking water for the day. So that's what we've got so far. And so I just want to talk about the triple bottom line. I always have my students consider the triple bottom line for all of their projects. So the definition of sustainability: people, planet, and profit. So in terms of people, we're helping human health. So both with respect to arsenic in our drinking water and indoor air quality. The planet, we're taking this waste wood and we're turning it into energy. And in terms of profit, the treatment cost per liter is about 25 cents. So you can compare that to what it might cost for you to buy a bottle of drinking water. So now that we've shown that we can make this positively charged biochar to remove negatively charged ions from water, in the winter quarter, we plan to start experiments removing fluoride. So this map shows fluoride prevalence in groundwater around the world. And so this is the next problem that we're going to tackle. So thanks for listening.